Hello everybody. So we are back to our plasma class again, and what we are dealing these days is fluid model, and we are now starting the energy conservation equation uh, from a phenomenological ground rather than going into a detailed mathematical derivation, taking the second order moment. We did up to first order moment, and we have done elaborate derivation of this momentum conservation equation, and there we obtained the apart from this momentum conservation equation, we got the generalized Ohm's law, and we tried to find out that how we can retrieve our usual Ohm's law from that, under what condition it achieves. Then we did with our this imaged equations and what are the ideal imaged equations. These things we tried to understand, and now we are dealing with this energy conservation equation. And in our previous class, we have dealt with this radiation laws, then collisional volumetric collision frequency, then collisional exchange term, then your J dot grad T energy transport mechanism, then thermal conductivity, so heat transfer to conduction. And while doing so, we have finally reached to one energy equation that I will come to. But before that, I think I missed one thing while describing the generalized Ohm's law. I'll just tell that thing what I missed probably. So let us come back to this. This was the generalized Ohm's law, and we got this topmost equation from addition of the momentum conservation equation for electrons and ion fluid component. So while we did, actually this term resulted in the current density, but you know that here this GAD PI and GAD P both are there, and this was having one negative sign, okay. And you know that Pi plus P actually gives you the total pressure. Now in a plasma, if it is only singly ionized, then the pressure contributed by the ions and that by the electrons, they are equal because they are equal in number, and if it is a thermal plasma, then they are having same temperature. So Pi is equal to Pe is equal to total pressure divided by 2, because the total pressure is basically contributed by these electrons and ions, okay. And the other thing that we used in this equation for simplification, that whenever equivalent terms are there, one is divided by Mi and one is divided by Me, because of the huge mass difference, more than 1800 times mass difference between these ions and electrons. Whichever terms, equivalent terms, actually one divided by Mi and one divided by Me, we just eliminate the term something that quantity divided by Mi and keep only the term that quantity divided by Me. So here actually you see that E GAD PE and E GAD PE, they are equivalent terms, and when one is divided by Mi and one is divided by Me, we just neglect this term. Similarly we did everywhere. These are the equivalent terms, E square Ne and E square Ni, because Ne must be same as Ni if it is to maintain the charge neutrality, and if it is singly ionized, then they are essentially equal in number, if it is fully ionized, of course. And even if it is not fully ionized, whatever electrons are coming, they are coming from the ions only, and they are single ions, so their numbers should be equal. So these two terms are equivalent, and one is divided by Mi and one is divided by Me. So whichever is divided by Mi, we neglect that and we keep only by divided by Me, because Me is much less compared to Mi. So that way we did everywhere, and wherever like E by Mi and E by Me is there, so we can just neglect this E by Mi and we can keep only E by Me, so that will be sufficient. So in doing so, we had these two terms GAD PI and GAD PE, and you note that in the derivation of generalized Ohm's law, we have used this thing and we have written only GAD P by twice Me. This is neither Pi nor Pe, it is the total pressure, okay. And that is this two factor, half factor rather in this, that appears only because we have now eliminated Mi divided by Mi term, we kept Me, and we have written that in terms of total pressure. So that is how it is. So I just wanted to remind you that this part probably I forgot to tell in that while describing that slide. So I finished that. So I'll now come back to our net energy equation what we are having now. So these are the different contributions that is appearing in the energy equation, and finally we reach to this steady state energy equation like this. Okay, why we say steady state? Steady state means that the system has reached an equilibrium and nothing is changing. Okay, for example, suppose in this room if you keep some heater, then temperature will start rising, and after certain time you will see that the room has been equilibrated to some temperature T, because there are many dissipation mechanisms and the heater is adding some heat, so you have got an elevated temperature, but that elevated temperature is now steady, it is not changing anymore. So the time varying part, actually whatever was there, that goes, and then you are left with this kind of steady state equation. So what it is giving, actually the left hand side is the convective term. You see that it is rho v into h, and the first one on the right hand side, this is the conductive term. Okay, so the energy transport due to conduction. Then this one is the J dot gravity term, as I already described how this J dot gravity term appears. This one is nothing but the Joule-Heating term. Okay, sigma E square. So sigma E square means equal to sigma you can write, then J square by sigma term equivalent you can write that. And then this one is the radiation loss term. So that is why the minus sign is there. So this radiation loss become important when a system is really at high temperature, say above say 10,000 degree Kelvin, then that plasma radiates significantly, so that you must include this radiation energy loss term. And I already described in the last slide that for argon plasma, say below 10,000, it is almost negligible, you can neglect it. But as you go beyond this 10,000, then it rises almost exponentially, and in this region it is really significant. So what we are doing now in steady state, we are assuming that quantities do not vary with time at a given spatial coordinate. The viscous dissipation terms are negligible. Here we have considered that. And then since the plasma is a high temperature system, we must include the radiation, due to radiation becomes significant and needs to be accounted. ER is the radiation loss, so you don't mix up it with this E electric field. This smaller of course there, but this is electric field and this is the radiation loss, energy loss by radiation. So the general equation looks like this, and now what we are now having, we have all the conservation equations, like we have the mass conservation equation, we have current continuity equation, we have momentum conservation equation, and now we do have the energy conservation equation as well. Okay, so what we can do now, we can solve this set of equations. But how to do that? Doing that in an analytical manner is very difficult. And in some very special cases only it is possible. Otherwise, you need to handle this using some numerical techniques. There are various methods like say finite element method, finite volume method, and if you are not aware of this thing, then I'll only tell the basic underlying principle in that, but not the details. For mathematical understanding and about this approach, like finite element and finite volume approach, you need to consult proper numerical technique books, where you will be getting idea about how these methods work actually. So there are basically three methods people are using. One is your finite difference method, which is very simple, and that concept you know, and the fact is that even though it is very simple, it can actually give you very accurate results No need to neglect this technique, finite difference, saying that it is very simple. Of course, it works for simpler geometry. If you are having a complex geometry, then handling those systems using this finite difference technique a bit cumbersome. But uh, in geometry, where it works well, there it will really give you accurate results actually. So I tell you that. Now, in case of fluid flow, you know that it is probably bit more convenient to handle those systems using finite volume approach. So what you do, you take those differential equation and do one step integration, and then or the your control volume, and then you solve those equations. So that is basically the finite volume approach. Now what I do actually, a numerical recipe. Now you know that we are this course is for your theory and application for thermal and non-thermal plasma systems. Okay. Now to handle that, we have gone through the basic plasma processes. We now understand that how a plasma behave. We went through orbit theory, we went through kinetic theory, and we have now reached to fluid model, and we have now gone through all the recipes that works there, all the your mathematical machinery that are involved there, and how to extract the information out of those mathematical framework that we have now understood. At least we have understood that the root we have understood. Maybe that we have not gone into very detail of your intricacies of each method, but we know overall that what are the equations that are involved there, and we are now in a position to understand those systems. Now comes actually how do we apply those equations to real life problems. So what I will do here, this is very much essential because we are handling the processing plasmas, not the textbook theory kind of thing. We are directly targeting the application area, and we are getting prepared through the theory just to attack that practical problem. So now we have now covered a pretty good part of the theory. So we are now in a position to attack the actual problem. How to apply those equations which we have learned just now into a system where which we are directly going to apply in the processing area. So there we start. So what we'll say actually, our approach is that whatever phenomena that is happening on the macro scale, they are basically governed by the Newton's law of motion and fundamental principles of mass, energy, and species conservation. This is looks very simple, but this is very insightful, and you can dive deep into the problem if you can understand this slide. Actually, you know, most of the motions in our real life problem, they are not relativistic. So Newton's law of motion works very well, and the three laws of Newton's law of motion actually it governs most of the mechanical motions that we are handling everyday life. Now the other thing that is universally applicable is the Maxwell's equation. And basically what we have done in our previous classes, in all the theories, if you go into deep of that, you will see that we have done nothing but only applied these two things, and we have finally got something, conservation equations, which are mass conservation, momentum conservation, species conservation, and energy conservation. So these are the basically conservation equations, and together with Maxwell's equations and Newton's law of motion, that completely describes the system. So this is the theoretical formulation, whatever we are seeing on the macro scale. Now, what we have done and what we are going to do, let me tell you that whenever we are going to do, we need to handle time and space. Okay, so what kind of time and what kind of space we are going to handle, we need to know the scale. Okay, Now, from the beginning, what we are doing, we are trying to simplify the things so that we can attack the problem realistically, so that the system remains manageable. Like we started with your orbit theory, it was pretty simple when we are assuming that collisions is not significant. But when we are coming to problem of practical life, we are seeing that collision is pretty enough there. So we must consider that. And then what we are finding that they are kinetic theory equations. They are describing the system in your 6 plus 1 dimensional system. So 3 velocity coordinates and 3 spatial coordinates and time. And we found that it is really a very complex system, and we are not in a position to handle all of them together, even with the kind of advancement that happened in the computational resources. So we told that let us simplify it, and we are really not bothered about the kinetics of the particles that are composing the plasma in the velocity space. Rather, we are interested in the movement of the plasma as a whole. Okay. Then what we did, actually we integrated over the all velocity space in the kinetic theory, and we obtained the fluid equations. So in the fluid equations, we obtained the momentum equation, mass conservation equation, and finally that has led to your this thing, what you call that energy conservation equations as well. When we have done this 6 plus 1 dimensional to 3 plus 1 dimensional transition from kinetic theory fluid model, are we now in a position to handle the system now as it is? Probably not. Why? I am telling you. You see that in a plasma, what are the time scales involved? The atomic transitions, they are happening in the scale of nanoseconds. You know that the lifetime of the these states, for the time with which it can stay in those levels before they make a transition. There are metastable states, of course, which has a longer lifetime. But if you want to include those things, that atomic transitions, molecular transitions, rotational, vibrational transitions, then you will see that you are essentially need to handle a time scale which is of the order of nanosecond. And then the fluid dynamic instabilities, like some fluid is moving from here to there and some instabilities are happening there. So those things are coming in the range of millisecond. Okay. So directly from your nanosecond, we are now jumping to your millisecond. Then when the fluid is moving from one place to another. So they are phenomena in the order of seconds. So in handling the plasma system, you need to cover a time range which ranges from nanosecond to second. So 9 orders of magnitude you need to cover in a time scale, which is enormous. And if some computing system wants to cover the complete range, that is, if you want to model a plasma, you need to cover up all the phenomena that is happening over there. Then you need to start from the atomic transition to fluid flow, that is nanosecond to second. And the range of time scale that is there, it is really enormous to handle with the computational resources that are available at present. So you now understand the complexity that is involved there. And then the spatial scale. Then spatial scale, basically, this atomic scale 2 meter. So you are essentially, if you are not considering the nuclear things, at least atomic transitions, atomic vibrations, you have to start from there. And if you start from there, because you know that kinetic theory when you are handling, you are not essentially including the nuclear transitions, but you are essentially considering the movement of your atoms and your molecules. So you need to handle those kind of spatial scale, that is angstrom, and to where you need to go to meter. So that 10 to the minus 10 meter to meter, that is a kind of spatial scale that you need to cover if you really want to accurately handle a plasma system completely as a whole, which is really not possible. So what we do, we try to model some phenomena and present that in some way. Okay. So that is why we call these as modeling. So this fluid model equations we'll be using, and here I tell in this slide that what are the different formulations we are using. So what we are doing, depending on the nature of the problem and the quantities of interest, the fundamental principles are expressed in terms of algebraic equations, ordinary or partial differential equations, or integral presentations. So that is essentially the fluid flow equations that will be there. And numerical simulation is by and large is the technique of replacing the governing transport equations, whatever you are there seeing, whatever you have formulated, with algebraic equations when you are discretizing those differential equations for simulation purpose and obtaining a final numeric description. You know that is a numeric description of the phenomena in space and or time domain. Why and or? This is because the under steady state simulation we can eliminate the time. We'll be getting only in the spatial coordinates. Okay, and why we are doing so? Because many of the times the systems finally operate in steady state. If it is not, then those kind of systems are not very much user friendly. If some system plasma system is now behaving like this way and next moment is behaving like that way, so it is unpredictable kind of thing. Such systems occur definitely in practical cases, but such system we will not like to get, because we need something which will be known to us. What are the process parameters will be known to us, which are not changing over time. Then only we will be able to promise a product after the processing, which will be having a desired property. Otherwise, we will always be uncertain about the end product, quality, and what throughput it may have. Okay, so always systems which are showing some sort of equilibrium behavior or steady state behavior, that will be of interest to all the process people and these process industries. Okay, so now what a numerical simulation means, the name itself is telling that it is numerical. Okay, behind those numerals actually there may be some phenomena which are resulting into those numbers. So in the simulation there is a black box at the center, which is numerical simulation, which is having some algebraic equations, simply the algebraic equation which have resulted from some differential equations which represents a process. Now, for the numerical simulation in a computer, that is a black box, and what you give as input are some numbers, and at the output also you get some numbers. So, irrespective of the nature of the problem, but the algebraic set of algebraic equations which you are handling in the numerical simulation, they originate from specific problem that you are handling, like it may be your arc plasma system, or it may be a radio frequency plasma system. So depending on that, this set of numerical equations, what your algebraic equations, what you are handling, they will be different, because your differential equations which are leading to those algebraic equations, they themselves are bit different. Okay, so this is what numerical simulation. You give some numbers as at input and you get some number as output. The numbers when you are putting, because you know the system, you know what are the parameters controlling the system. So those the values of those parameters you are putting as input. So they are the numbers, but you know what numbers to put there. And at the end, whatever the numbers that you are getting out, now it is your time to explain why those numbers are coming out for the system that you have modeled in the numerical simulation part in the center. So those algebraic systems what you are solving now, they basically originated from the problem that you are attacking. Okay, so now you got some numbers, and those numbers you need to interpret to explain the behavior of the system that you are handling. So, in non-equilibrium modeling, this when you are handling the fluid model, to reach those equations, we started with the kinetic theory model, and we assume that there are two fluids. One is your ion fluid and one is electron fluid. But in practical case, there will be electrons, ions, and neutrals. Both will be there. Even though if you consider that processing plasma doesn't involve very high temperature, then you can restrict yourself to a very good approximation to up to the fast ionization. There is no problem. But you need to include the neutrals if they are there. Okay. Now, here under the two fluid model, what we are doing? Electrons follow temperature TE, and all other heavy species, whatever there, including the ions and the neutrals, they follow a temperature TH. So it is a quite simplified model. There are two interpenetrating fluids. One is electron fluid, another is ion or heavy species fluid, which are interacting with each other and trying to equilibrate. So one species, the electron species, is presented by temperature TE, and all other heavy particles are presented by the temperature TH. Now in the system, two separate energy equations now exist. One for electrons and the other for ions, atoms and the heavy particles. So all of them together are represented by one equation, and electrons are presented by another equation. So electrons are receiving energy in this model. Electrons are energy, they are receiving energy through ohmic heating. Okay. Now you know that the same principle as your in solid conductive system, the heating occurs the same way. The plasma is posing some resistivity depending on the kind of plasma that has been created, and when the current is passing through that, the electrons are receiving energy from the field. Then they are getting heated, they are increasing their temperature from the field that has been applied, and then they are heating the heavy species, whatever is there. That may be your ions or it may be neutrals. Now, in this model, what we assume that there is no ohmic heating in the heavy particle energy equation, because electrons are fast, they are moving. Like in a this solid, we assume that the heating is by the electrons only. Okay, electrons constitute the current, and we know that how to how to calculate the J square by sigma, that is the amount of energy that is getting dumped into the system. Okay, so same way we assume here that the electrons are only contributing to the heating, and the heating term is absent in the heavy species equation. Like when we are considering the neutrals, there is no question of heating at all actually, and because it is chargeless. And then if ions are there, they can respond to the electric field, but what happens actually, and the current constituted by them will be negligible because they cannot move very fast, they are extremely bulky. Then viscous dissipation term appear only in the heavy particle equation. Okay, because the electrons are highly mobile, and the viscous dissipation, what it takes care, it is the frictional force. When one layer tries to slip over the other layer, this force appears and this causes the heating. Okay, so that will appear only in the heavy particles. You understand that when a gas is moving, it is basically the atoms which are moving. So this viscous term appears only in the heavy particle equation, and radiation loss appear only in the electron energy equation. So these are the consideration that we will include in the system, and why radiation appears in the electron energy equation, because the radiation whatever is coming out, that is because of the transition of the electrons only, okay, in the atoms. So when we are taking care of that, then we will include that in the electron energy equation, and then we will find what is the ultimate energy equation that appears, and we will handle that in the next class. So for now, we will see you in the next class. Thank you.